My name is Jason. I'm from Harvard University, and today I'm presenting for you NeuroBench, a framework for benchmarking neuromorphic computing algorithms and systems. I'm giving you this presentation, but I'd like to point out that this is quite a large community effort from an open community of neuromorphic researchers representing academia and industry. Thank you to all my collaborators, some of whom are in this room now. I'd like to start with a little bit of a silly example to get us all on the same page on what is a benchmark. So, okay, here we have three figures. One tells you I'm fast, one tells you I'm real fast, and one tells you me most fastest. Now, the question is, what does fast mean? And it can mean different things in different contexts. So, of course, we can have fast on land and fast in water. Benchmarks, such as a 100-meter dash, a 100-meter swim, will standardize what performance means and how it is measured. So this is the way that you can define what fast means between these two characters. And of course, benchmarks also provide a way to rank and compare performance to separate out the Olympians from the viewer at home. Now, into a more serious example of a benchmark. This is a classic benchmark from deep learning, ImageNet. ImageNet as a benchmark for deep learning, of course, they opened this challenge along with the ImageNet benchmark. And over the years, you can see how progress was made. The essential components of the benchmark, of course, are the task. In this case, for ImageNet, it was image classification. The data sets. So for here, it was the corpus, the ImageNet corpus, and the metrics which are measured, top one classification accuracy. And you can see over time, this benchmark, ImageNet, aligned researchers on challenges of interest, measured state-of-the-art and growth in the field, and spurred research progress forward. Terry on the first day gave this as an example, where here in 2012, AlexNet sparked deep learning by showing this humongous drop in error. And I will hammer this point home that standard benchmarks are vital for technological progress. Now we can talk about benchmarking for neuromorphic computing. I've just shown you a deep learning benchmark. But of course, there are issues with standard deep learning benchmarks. ImageNet, for example, lacks this native temporal dimension. It's an static image classification task, which is not in tune with many of the neuromorphic approaches. There do exist prior benchmarks in the field, such as NMNIS, DVS gesture, SHD. And though these have been used and adopted, there are still issues related to widespread standardization of benchmarks across the field, which has led to calls to action for benchmarking in neuromorphic computing. We identified three challenges in benchmarking neuromorphic computing. The first is a lack of a formal definition. So I have another silly example for you here. You can take the word neuromorphic, and to an outsider, this may mean simply biologically inspired. And you take a look at this, an ANN, and you say, well, it's called a neural network. It's biologically inspired. And okay, GPT-4, that's an example of an ANN. It runs on GPUs. Well, all of deep learning is neuromorphic. Right? And more seriously, as we all know, there is a wide variety of diversity when it comes to the research topics in the neuromorphic field. And this leads to the question of what should be benchmarked as neuromorphic. How can we formally define neuromorphic computing so that we can build benchmarks for it? And the answer we came to is we shouldn't do that. We shouldn't formally define neuromorphic computing because this will limit the features that are of interest to the benchmark. So this challenge necessitates inclusive benchmarks, which have general tasks of interest, general metrics, and allow for direct comparisons with conventional approaches. Direct comparisons along the field of neuromorphics as well as with conventional approaches. So this challenge necessitates inclusive benchmarks. Next is implementation diversity. Along software frameworks, there exist many different software frameworks which are used, which have different goals of, say, neuroscientific stimulation, hardware interfacing, or automatic SNN training and configuration. In hardware, of course, platforms differ in terms of circuitry, scale, flexibility, and programmability. With this implementation diversity, benchmarks require actionable portability and standardization. It doesn't matter if I tell you that I have great results on the task that I was able to implement if you aren't able to implement that yourself as well and compare your results against mine. The second challenge necessitates actionable benchmarks. Thirdly, rapid research evolution. In one of our NeuroBench community meetings, we asked the community, what topics should a neuromorphic benchmarking workshop include? And these are some of the results that we got. So you can see all types of different answers here. This once again goes to the point of diversity in neuromorphic approaches. Sparsity, selecting neural networks, optimization tasks, online learning, deep learning, continual learning, everything. Given the range of topics here, it doesn't make sense to build one benchmark and then keep it static. A benchmark should grow over time to include more and more of these features. Benchmarks must be iterative to capture these features of interest and evolve with the state of the art. This is along the lines of benchmarks in other fields, such as the SPEC benchmark for CPUs and MLPerf for machine learning systems. So our three challenges necessitate inclusive, actionable, and iterative benchmarks. And with this, we present NeuroBench, a framework for benchmarking neuromorphics. Now, with these goals, what we have done with NeuroBench is invited an open community of neuromorphic researchers and asked them the following questions. What are the benchmarks of interest to drive research? What are the common tools to be developed? And what are the initial set of baseline approaches that we can take for these benchmarks? For NeuroBench, we adopt a dual track structure. So how do we approach benchmarking for algorithmic and deployed methods? The dual track structure involves the algorithm track, which is system-independent complexity analysis, and the system track, which measures methods deployed on hardware. The algorithm track includes these general metrics for model complexity and proxies for hardware performance. There are, of course, limitations to proxies for the algorithm track, but another benefit of this separation is that the algorithm track allows for exploration and prototyping without the need for implementation to neuromorphic hardware. While a lot of neuromorphic algorithm research occurs on non-neuromorphic platforms such as GPUs, CPUs, we can use the algorithm track for this prototyping for methods which may someday be implemented onto mature neuromorphic hardware. That is not to say that neuromorphic hardware doesn't exist, and that is why we have the system track, in which we evaluate deployed latency, throughput, and energy efficiency. Right, so for each of these benchmark tracks, there is this standard tasks and measurements. So the data set or the task is defined. The user defines the solution, which is the algorithm for the algorithm track, or the algorithm deployed to hardware on the system track. And of course, at the end, you get common metrics. Between these two tracks, highly effective solutions can motivate future solutions in the other track. So there can be this co-innovation between solutions. As an example, best performing algorithms are target workloads for future hardware, and the hardware influences network topologies, et cetera, on the algorithm track. Meanwhile, between the system metrics and the algorithm metrics, deployed performance can inform hardware models of algorithm complexity metrics. This is to say, when we get these complexity metrics out of pure algorithmic benchmarking, we can compare these to how the deployed metrics look on the system track. And from this, we can create a hardware model for algorithms. So we can determine, say, the operation costs or compute and memory resource costs. All right, now I will dive into our algorithm track. From the algorithm track, we introduced the V1.0 suite of benchmarks. This includes 4 novel benchmarks to the neuromorphic field. The first is keyword few-shot continual learning. This is the application includes continual expansion of a multilingual keyword dictionary using few training examples. We take the data set, the multilingual spoken word corpus. This is a giant data set, over 6,000 hours of speakers speaking in many different languages. The task is for the model to base train on 100 keywords across 6 base languages. This forms your initial dictionary of 100 words. Then, successively, it will undergo 10-way, 5-shot learning sessions to learn a total of 100 new keywords from 10 new languages. At the end of the benchmark task, the model that you have trained should know the initial 100 keywords as well as the 100 new keywords. So the model knows 200 keywords by the end. This is the continual learning aspect. The correctness is measured in classification accuracy, measured after each session on all previously learned classes. This is a standard benchmark in deep learning continual learning fields. However, previously it was used for images, a static data modality, and we apply it to audio, a temporal data modality. Next, event camera object detection. The application here, real-time, energy efficient, or always-on automotive object detection, or autonomous driving. Here, we also take a very large data set, the Prophecy 1 megapixel automotive detection data sets. So uncompressed, this is 3.5 terabytes, but realistically, you would be working with something more along the lines of 80 gigabytes. So here's examples of the Prophecy data set. So you can see it's a car driving with an event camera, and the task is to detect these objects, such as people or other cars. The correctness metric, of course, is COCO, mean average precision, which is a standard metric in object detection. Next, a motor decoding task. The application here can be in sensory motor biophysiological emulation, for example, for use in prosthetics or brain-computer interfaces. The dataset includes the motor cortex recordings of 2 non-human primates who are engaged in reaching tasks. So they are shown a screen with dots, and they are engaged in reaching tasks to touch each of these targets in this grid. So given the cortical recording time series from the monkey's brain, the task is to predict the fingertip reach velocity in the x and y dimensions. And the correctness here will be the r-squared of the predicted velocities. Finally, the 4th task is this chaotic function prediction. This is a synthetic data task. Applications are in dynamic time series forecasting. So for example, in markets, climate, signal processing. Also, this is a small dimensional problem, which may be useful for prototyping emerging resource constrained hardware. So for example, mixed signal hardware. The data set is the Mackey-Glass time series, which is a one-dimensional nonlinear time delay differential equation. Essentially, it's just one function. And the task is to train using the first half of the generated time series and then autonomously, regressively forecast the second half. Correctness is measured here in symmetric mean absolute percentage error. All right, so I've shown you the benchmarks, and now I can show you the metrics, which are of interest for the overall framework. So on the algorithm track, we have the following metrics. There are solution agnostic metrics, solution agnostic in the sense that they are general. As long as what you're putting in looks like a neural network, these metrics will apply. So of these solution agnostic metrics, there includes correctness, which is defined per task, and complexity. So these are general metrics, which reflect the architectural cost of the algorithm. I'll get more into this. In addition to these solution agnostic metrics, we can have solution specific metrics, which make certain assumptions about what you are benchmarking, so the solution type. So for example, we can define a solution specific metric such as the complexity of neuron dynamics. So if you expect or assume that you have a certain hardware model, you can say, based on this hardware model, we can understand what the neuron dynamics look like and define a complexity metric based on that. Another solution-specific metric might include robustness to noise for, say, methods aimed towards analog hardware. This could be a metric where you implement it by perturbing or adding noise and then seeing the effect. So into the solution-agnostic complexity metrics, I will define the following: footprints, memory usage, accounting for quantization, parameters, and buffer requirements. And then 2 types of sparsity, connection sparsity and activation sparsity. This is sparsity of the model synaptic connections, which accounts for pruning, but also sparse initialization. So say when Katie Schumann was presenting her hairball, that would be an example of sparse connectivity. There's also, of course, activation sparsity. This is the sparsity of neuron activations during execution. So here, this can give insight into the deployed communication requirement. Next is synaptic operations, which is further subdivided into the following. The number of synaptic operations per prediction can be divided into the dense synapse. So this accounts for all synaptic operations, including zero operations, and would be the case if you were implementing, say, dense matrix multiply on a GPU. Then we have effective synapse. Effective synapse count only the non-zero operations. So when you take into account your sparsity of connectivity and activations, the effective synapse will give you that number. The effective synapse is further subdivided into multiply accumulates for valued activations and accumulates for binary spikes. So one advantage of spiking neural networks is that the activations are binary, and this can reduce the complexity of your hardware. So we separate out multiply accumulates from regular accumulates. Finally, there is model execution rate, which has a little bit of a star. This is the throughput of the model output, which reflects the responsiveness and deployed compute requirement. So this is not necessarily a metric to be calculated, but it is a critical algorithmic feature that should be reported with your algorithm, which gives a better insight into its complexity when deployed on hardware. All right, so next I will look into benchmark case studies. These are algorithmic baselines. These are not meant to be state-of-the-art research tasks, but are instead meant to show you how difficult the novel benchmarks that I've presented are and what kind of opportunities still exist towards solving these benchmarks. First off, in the case of the keyword few-shot class incremental learning, the continual learning task, we can see the following base metrics, and I'll point your attention to a couple of things. First off, the footprint. So, okay, first we can see the accuracy, which is measured between an ANN and an SNN. The accuracy numbers I'll get into on the next slide, but let's take a look at the footprint. We can see that the SNN is about double the size. But when we look over at the synaptic operations, we see that the SNN is quite a bit more efficient when it comes to the synaptic operations done in order to produce each of the predictions. When we're looking at the model execution rate, this is the reason why I was making a point about this. This is not a metric that is calculated. This is a feature of the algorithm. So the ANN takes the entire 1 second sample and processes over it all, while the SNN processes over 200 time steps. Just looking at these numbers, you can say what would be the hardware requirements in order to deploy this type of method. On activation sparsity, we can see, of course, the SNN quite sparse in its activations. Another thing you might notice is that we have connection sparsity here at 0. We didn't prune any of these models, but there is still optimization room in there. Now, for those interested in the continual learning aspects, I won't explain these results too deeply, but these are the accuracy curves over the continual sessions. And you can see these dotted lines represent if the models were frozen at the base session. So if we didn't do any incremental learning at all, this would be the accuracy over time. And you can see with this prototypical approach, we improve on this accuracy by quite a bit. You can see, though, that while the slopes of these curves between the ANN and the SNN are relatively equivalent to each other, there is this large initial drop between the ANN and the SNN, especially with the SNN compared to its base performance, which is the top of this dotted line. So like I said, I won't get too deep into this, but the idea is that there are opportunities towards a more general feature extraction from the SNN based on these types of results. Please refer to the paper, or you can ask me after if you're more interested in these results. I'll move on. So this is the event camera object detection task, and the table looks quite similar. Like I said, these metrics apply broadly across all of our different benchmarks. So I will point your attention to the footprint. We have an ANN and a hybrid model. This is a hybrid ANN and SNN. The ANN component does the feature extraction, and the SNN component turns those features into those bounding box predictions. In terms of the footprint, the hybrid model is quite a bit smaller. In terms of the activation sparsity, however, it is actually less sparse, this hybrid model, than the ANN. which may point towards the SNN components of this model not doing their work in pulling up activation sparsity. And when we're looking about the ratio of effective synaptic operations in the model, you can see here from the total dense operations, the effective multiply accumulates in the hybrid model are very high. Meanwhile, the accumulates are much lower. In this case, just from looking at this table, we can extract the information that the SNN component of this hybrid network is not doing very much compared to the ANN component. And based on this, we know where do we have optimization opportunities. Next, we have our neural decoding task for the non-human primates. The reason why there are two lines is because there's two different primates. So there's data for primate number 1 and primate number 2 for an ANN and SNN trained. This was a very surprising result that we were able to generate as a baseline for the SNN. You can see here that the footprint is not much different between these two. However, the activation sparsity of this SNN is ridiculously high, and that leads to an effective operation count per regressive prediction of hundreds of accumulates when we account for only the non-zero operations. This is quite impressive. Okay, but furthermore, we conducted a few more experiments with this benchmark. The ANN and the SNN are these unhighlighted results here. And based on the accuracy of R squared, you can see that as we increase complexity towards more large models, so the footprint of the models goes up and we can generate higher accuracy on that. And here the effective synaptic operations can go up for these models here, and we can get higher accuracy there. So you can see how this benchmark provides the framework to take a look at your results and make very simple observations about what can be improved. Finally, I'll take a look at the chaotic function prediction task, the autoregressive modeling task. Here we benchmark a reservoir network, the echo state network, as well as an LSTM. And I won't get into any of these details, but I'll show you that this is the first example of where we have connection sparsity in our network for the reservoir echo state network. All right, so now that I've shown you some benchmark baselines on the numbers that we have produced, I'll next show you the algorithm track harness. This is the most important part of this talk. It is a software framework that is available for you to use and interface with these benchmarks. The harness is composed of a simple interface. The inputs from the user level include what model, the trained model that you'd like to benchmark, the data set and data loader, pre-processors, post-processors, as well as the metrics you'd like to get out. The harness will take this from you and go through the runtime where it actually runs through the testing data. And then at the end, give you the metrics, so footprint, connection sparsity, correctness, activation sparsity, and synaptic operations. The harness is extensible to new tasks, metrics, and frameworks. It is modular, and it is designed for easy development. This is of utmost importance for the harness to be used in this field. Using the harness is very simple. Simply install it as a Python package, pick the data set you'd like to use, train your model, define whatever processors you'd like, and then run the benchmark. So here you can see a coding example for the task, which is Google speech commands. Like I said here, import whatever you need, define your data, load in your trained model, define the components, define your metrics, put that all in. I'll show you one example of the simplicity and modularity of the harness. For the synaptic operations, one detail is that when we calculate synaptic operations through the harness, this is calculated exactly. Many other synaptic operation calculators exist, which you can find, but all of the ones that exist are formulaic. So based on the layer type and sparsity average metrics, it will formulaically give you an estimation of the synaptic operations. We decide to calculate synaptic operations exactly because when you have things like very irregular connection patterns and activation patterns, we would like to have exact synaptic operation measurement in order to see what is the exact number there. So this can be slow since it is an exact operation. So you can see here with one line of code, when we have activation sparsity and synaptic operations being measured, we have a high runtime. And simply by changing one line of code, we can improve our runtime. It's modular, it's simple to use. The harness is open source. There are tutorial notebooks. There's reproduction scripts for all of the baselines. So all of the results that I've shown you, you're able to go and reproduce those scripts right now. And it's very well documented. So here are some links to get you to NeuroBench, or simply if you Google NeuroBench, you'll find out all of this. So that was the algorithm track. Now I'd like to move into the system track. The algorithm track is very well matured, and I will present to you the challenges in benchmarking actual hardware. Neuromorphic systems come in many different shapes and sizes. So we can, for example, have here an edge board. The same type of neuromorphic core can be planted into a board and be made into an accelerator type situation. And furthermore, many of these boards can be involved in a multi-board system. So along neuromorphic hardware, there is this wide system variation from scale, milliwatt to kilowatt machines, form factor, standalone and accelerator boards, maturity in terms of whether it's a development research type board, a prototype, or ready for commercial use. So along all of this system variation, there poses some challenges in benchmarking the actual systems. So our goals for the system track is to produce shared guidelines across this wide system variation. And what does this mean? For the system track, we want to provide application level benchmarks, end-to-end benchmarks, where we can analyze from the top level what is the performance of each of these systems. This is in contrast to if we were defining micro benchmarks, which would go deeper into the hardware and make more assumptions about what is going on. Of course, we would like to have performance and efficiency measurements well-defined, how to get these measurements as well. The algorithm that's on your system can be open for this benchmark. And of course, there is also open pre and post processing. This means that the algorithm can be tailored to whatever hardware features. We aim towards component granularity results. So for example, if you have an accelerator board, we aim towards benchmarking the host CPU, any pre and post processing units separately, so that you can transparently analyze the benchmark results. And on the topic, transparency before consistency. In a place with much more mature hardware, we would be able to get very consistent setups for system benchmarking. Where we can't have that with these early development boards, we'd like transparency. So you go to a place and you see the numbers and you can read how were the numbers produced. This enables intuitive analysis of these widely varying systems. The system track v1.0 is a collaboration between different hardware vendors who are interested in head-to-head benchmarking. And these are a couple of the benchmarks which they first defined that they were interested in. First off is acoustic scene classification, and the next is this optimization QUBO task. For the acoustic scene classification, this is a more of an edge type task, always on audio smart sensor in various environments with a kind of milliwatt power range. The data set used is a common data set from the edge computing community. It is the DCASE urban acoustic scenes data set. The benchmark scenario includes a single stream. So the audio is coming in one sample at a time, batch size one processing. And the metrics are the classification accuracy, latency per sample, and energy per sample. Next is the optimization task. This is the QUBO type of task, solving a max independent set. So the applications, of course, in optimization, it is, of course, a scalable type of task with applications in finance, routing, scheduling, in both the edge milliwatt range and the large cloud kilowatt range. The data set here is synthetic graphs of various sizes and connectivity. And for the benchmark scenario, we'd like to run optimization tasks where the solution improves over time. The different type of neuromorphic hardware will have this easy an intuitive setup for optimization problems where you set up a inhibitory type network, and as the neurons inhibit each other, they will reach this steady state of firing, which represents your solution. So as the solution improves over time, the metrics include the most optimal solution that you can find, as well as latency and energy to reach various threshold optimalities. The system track V1.0 is ongoing. So once again, our target is toward transparent, rigorous comparisons of these mature and optimized neuromorphic hardware platforms on identical tasks. This is in the works, and it is something that's very, very difficult to produce. I'm very grateful for the system track members who are assisting with this. And with this, we'd like to provide the foundation for understanding and measuring further neuromorphic systems. We are starting out with these very mature, very optimized neuromorphic hardware, which are perhaps commercial ready. And if you have hardware of your own, I'd like you to go, when that is ready, to read that documentation about how we benchmarked these different systems and have you apply it to your own benchmark hardware. Like I said, this is still under works, but to show you speculatively what the system track benchmark tooling might look like, it is a simple addition to the algorithm track harness, which is here in red. This is what I showed earlier. So the pieces in blue and purple are the additions for the system track. So they include, of course, compiling and mapping the network down to the hardware through, say, various intermediate representations. There is the execution and measurement, of course, loading data and deploying this onto the machine, and then reporting the results. And I can point out here that these intermediate representations, which are speculatively a part of the NeuroBench system benchmark harness, can involve other projects such as the neuromorphic intermediate representation. Like I said, this is still under works, but happy to open dialogues for communication. All right, so I'm going to present ongoing work. What I've presented to you, especially in the algorithm track, is very ready to use. But as I showed in the beginning, this is an iterative process. We can't expect that our benchmark framework will be perfect immediately. So there's this still ongoing work. The repository is being actively maintained by myself and some of my collaborators. The system track V1.0 results are underway. For the algorithm track, we have this closed loop extension, which my collaborator Cornel is working on. You feel free to ask me questions if you're interested in this. We have closed loop extensions to classic RL tasks, as well as the primate reaching neural decoding task. So this is of interest in many cases. Also, with the neural decoding task, we have a challenge that we have set up at BioCast 2024. We're working towards producing common leaderboards. This would be one place where you can go and look at the results, the state-of-the-art results on these different benchmarks, see what they've done, and then move towards improving what they've done. And I'll be at Telluride and happy to talk and give a tutorial about NeuroBench there as well. In terms of other future work, which was of interest, data sets integration. So for example, integration with the Tonic library, which is a library for neuromorphic data sets. Metrics for neuron dynamics. These would follow along the lines of the solution-specific metrics that I presented earlier. Continuous time benchmarking. Currently, our algorithm track expects kind of digital, discrete time steps evaluation. So we can move towards continuous time benchmarking as well. And finally, open source hardware benchmark infrastructure through the system track. All right, I'm quite early, but I'd like to give an acknowledgement. We have a large open community of researchers who provided their time, energy, and wisdom to this project. So I'd like to highlight Cornel, who's in the audience today. He came with me to NICE. He was my collaborator in the weeds, helping to build these tools. I'd also like to shout out Eunice, who is also here at the NICE conference and helped to produce the LSTM baseline results on the chaotic function prediction task. And of course, everyone else, my advisors, Charlotte and Vijay from TU Delft and Harvard. It is mostly their wisdom that I am reciting to you now. that guided this project. As a summary, for NeuroBench does algorithm and system benchmarking. It is a benchmarking framework for algorithms and systems. It is associated with novel benchmark tasks, and it is extensible with its open source benchmark platform. The tools are there and ready for you to use. And I'd like you to listen in on the future, say at NICE 2025, and hear these types of thoughts. We demonstrate top of the leaderboard accuracy or synaptic operations on this particular task. We combine our method with this other project and show an improvement of. We open source this new task through the NeuroBench harness, so it is available for the community to use. Or compared to this project from last year's NICE, we have improved by, and filling it, a vision of the future. And now is a call to action. So finally, NeuroBench is this community-driven benchmark framework. It has been community-driven and it will continue to be community-driven. I'd like to place this in all of your hands. V1.0 is ready and still being actively extended, and we would like you to engage with the project. Check out our website for all the links. Thank you.